Questions? Next week is the final. It's going to be on Wednesday, a week from today. It's going to be mostly multiple choice. There's some things, though, that are difficult to test with multiple choice, like a wedge dash diagram, for structures. So you may have like a wedge dash diagram that you'll have to draw. Things like you'll have to know tetrahedral.
Are you going to be available
Triple planar.
for emphasize on Zoom over the weekend or anything like that?
Yeah, I could do that if you want the Zoom office hour. We'll have to figure out one.
I have a question, just in general.
Well, let me just finish with the other things. Chemical reactions. You may have to do some basic chemical reactions. Nomenclature. Energy level diagram. Those types of things are difficult to do using multiple choice. And so the bulk of the test will be multiple choice. There may be some free response ones, not many, but some free response. All right, sorry, Dan. What was it?
Oh yeah. So would chloroform be polar or non-polar?
Chloroform is a strange one because you would say it's polar, but and if it's polar, it should dissolve in water, right?
Mm-hmm.
But there's a problem with chloroform. I guess maybe it's not such a problem, but when we look at the solubility in water, it's minimal. And so let's take a look at the solubility in water. And so you'd expect it's tetrahedral, and the molecular dipole would be pointed straight down here, in this wedge dash diagram. Because chlorines are more electronegative here. If you look at the solubility in water, 10.62 grams in a liter. Usually when you mix chloroform with water, some will dissolve. At 20 degrees, it's 8.09 grams per liter. But the bulk of the chloroform, it's dense, so it sinks to the bottom. So you end up with two layers. When you mix chloroform with water, some of the chloroform dissolves. Most of it just sinks to the bottom and makes a chloroform layer here at the bottom, and then we'll have a water layer. This is an experiment that you do in Chem 1A. In Chem 1A, you do a redox reaction in which you form some iodine. And what you want to do is you want to extract the iodine from the water layer into the chloroform layer. The chloroform is a lot less polar, and iodine is totally non-polar. So iodine preferentially dissolves in chloroform. And so what you do is when you dissolve the iodine in chloroform, it turns it bright purple. And so this is qualitative analysis for iodine. It's a Chem 1A qualitative analysis that we do. And so, chloroform is polar, but it's one of these ones that doesn't really dissolve much in water. If we look at the solubility, it's soluble in benzene. Benzene is totally non-polar. It's miscible. That is, it's 100% soluble. Diethyl ether, oils, Lagrange, these are all non-polar. Diethyl ether is polar. Diethyl ether is, you got dipole forces. There's no hydrogen bonding in diethyl ether. Only the carbons are bonded to the oxygen there. The oxygen is that red one in the center. We have two alkyl groups attached to it. Oils are totally nonpolar. Lagrange is totally nonpolar. Alcohols are polar. Chloroform, this is not chloroform, this is carbon tetrachloride. Carbon tetrachloride is totally nonpolar. Carbon disulfide is totally nonpolar. And so it's a weird one. So don't worry about the solubility of chloroform, but it is polar.
It is polar, and you said what type of force is it?
Dipole.
Dipole.
double dipole, and this has one of the things that chloroform would have. You'd expect it to have very large what? It's going to have a pretty decent dipole. It's going to have a pretty decent dipole because chlorine's a lot more electronegative than carbon, but you'd expect it to have fairly strong what? Because it has a lot of electrons. Yeah, you'd expect it to have very strong instantaneous dipole. And that gives it, it's probably what leads to the property that it's pretty soluble in nonpolar solvents as well as polar solvents. And so it's a bit more complicated than we like to get into in Chem 4, so don't worry about it too much. Okay.
Strong instantaneous what?
Instantaneous dipole. Because chlorine has a lot of electrons. And you got 3 of them. For instantaneous dipole, those books base it on the molar mass. And so if we look at the molar mass of chloroform, the molar mass is 119. It's pretty big.
Going back to courses, when you look at water and ammonia, they act the same, right?
Yeah, water and ammonia are miscible in one another.
But for water, wouldn't that be considered hydrogen bonding?
Yes, water is.
So why would it be polar?
Why would it be polar? Because hydrogen bonds are unusually polar. The reason we call it hydrogen bonding is because it's unusually polar. Unusually polar. Pole comes from dipole. Dipole comes from having 2 poles, like a north pole and a south pole. But in this case, it has a positive pole and a negative pole. And the bigger the dipole, the more polar it is. And so hydrogen bonding comes from these unusually large dipoles that form when hydrogen is bonded to oxygen, fluorine, and nitrogen. And so it's extremely polar. That's why we call it hydrogen. So water is very polar. In fact, the polarity of water is often talked about in. If you look at a biochemistry book, chapter 1 of biochemistry book talks just about water. And that's one of the properties. This polarity means it can dissolve a lot of minerals. Minerals are important, electrolytes. We need potassium, we need sodium, we need all these electrolytes to properly function. And so that's one of the unique properties of water. It can dissolve these minerals because it's so polar. Minerals are very polar. Minerals have an ion, positive, and a negative. Ionic bonds are the extreme polar end. If you recall, we ranked these bonds from totally nonpolar. I think they use nonpolar covalent. This is polar covalent. This is ionic. And so it's based on electronegativity. The delta En here, the difference in electronegativity is 0. And so this is delta En. This is non-polar. The delta En here is growing. It's more significant. Here, the delta En is one of the largest values you can have, which creates an ionic bond. This is the most polar. Here. This is less polar because we don't have full charges. This is what we call partial negative, partial positive charge. This is totally nonpolar. There's no charge here. These charges we look up in Chem 1A. We look at these charges in terms of something called electrostatic potential mass. And we looked at these already. Let's hope they pop up the image here. So we're looking at different polarities here. HF would be the most polar because fluorine's more electronegative. So you can see it's more red here. Red normally, and now we're getting into chapter 19. Normally when I think red is usually in batteries. Red is usually reserved for the positive or the negative terminal of a battery.
Positive.
Yeah, usually we use red for the positive terminal of a battery. But in electrostatic potential maps, somebody decided to make red not positive. They decided to make red negative. I don't know why,
Fantastic.
but I always thought that was pretty annoying.
That is nice.
Anyway, red is negative and blue is positive and green is neutral. So you look at something like HI is pretty nonpolar. The difference in electronegativity is minimal. And so HI is fairly nonpolar, and then polarity increases as we go. Now, hydrogen puts up a pretty good fight because hydrogen's electronegativity is right in the middle. It's between boron and carbon. You want to put hydrogen in the periodic table as far as the ranking goes. And so hydrogen puts up a good fight, but sodium's on the left side. You know, sodium's electronegative is like 0.6, 0.7, whereas hydrogen's like 2.1. So sodium's easily going to lose a tug of war with chlorine. The hydrogen won't. And so we see these electrostatic potential maps are very useful. These electrostatic potential maps are generated from the Schrodinger equation, quantum mechanics. And so usually we put these through quantum mechanical calculations, and this is what it spits out, the computer spits out for you. Here we can see positive over here. There's actual numbers to these. We can get the number, the charge on that. And so here we don't really get the charge, we just say delta, meaning some partial charge. But when you put these into quantum mechanics, we actually get a number for these values. Yeah. All right. Other questions?
Yeah, so when you're looking at, let's say water, just to make it easy, we're at, like close to sea level, and you go to the mountains, right? So one is higher boiling point than the other, and does that have to do with the pressure?
Yeah, that has to do with the pressure. One thing, I'm not going to make you memorize this, but there are a whole bunch of curves. And how do you remember the curves? You look at them. Like if you looked at the curves every day, then you know all the curves that we've covered in class. Do you recognize this curve here? The piece of H2O versus temperature curve. If I looked at it every day, I'd remember what it looks like, the curve. What does it look like? Normally when pressure versus temperature in the gas chapter is linear. It's just a straight line. It's not a curve. This is ideal gas. And so when we double the temperature, we should double the pressure. If we triple the temperature, the Kelvin temperature, we should triple the pressure. That's a law. That law is Boyle's law, but you don't have to know the names of these particular laws. Or is it Boyle? I don't know. No, Charles' law is not. Charles' law is important. You should know Charles' law. Why? Charles' law is relevant because that's the original.
That's the original ideal gas law.
No. That's the original verification for absolute coldest temperature possible. The proof, the original, evidence for this coldest temperature. Coldest temperature would be minus 273 Kelvin. Minus 273 Celsius, which would be defined as 0 Kelvin. So anyway, the curve, it looks like this, and it's because we're looking at not just a gas, but we're looking at both a liquid and a gas. And as the temperature goes up, of course, the pressure of the gas is going to go up. But also, as the temperature goes up, the vaporization rate goes up too. And so the temperature is going to have a dual impact. It's going to increase the pressure of the gas. That should go linearly, but at the same time, the population, the number of gas molecules is going to increase with increasing temperature. This is what causes it to go nonlinear like this and increase more exponentially. This is very important because this tells us the boiling point at any boiling point's a temperature. It tells us the boiling point at any pressure. So normal pressure is 1 atmosphere, so normal boiling point is 100 degrees C. But what people like to do is they like to buy these pressure cookers. The pressure cookers maybe aren't so popular anymore. I remember going into the kitchenware place and saying pressure cookers all the time, but I haven't seen pressure cookers that much anymore, so maybe they aren't as popular as they once were. But pressure cookers, you can get this lid, and then as you heat water in the pot, you build up pressure because this lid seals it. There's a safety, of course, there's safety because you don't want to build too much pressure so that it explodes. But maybe there were hazards in the past. But the higher the pressure, the hotter the temperature. There's a rule of thumb that I learned in Chem 4, and I still remember this. And that is, for every 10 degrees C temperature increase, your cooking rate doubles. So if you cook pasta at 100 degrees C versus cooking pasta at 110 degrees C, the pasta cooks twice as fast at 110 degrees C. And so that's a rule. It's not perfect. It's just a rule. There are exceptions to the rule depending on how hard it is to cook things, but simple things, you expect that. And so pressure cookers. Likewise, if you let's say you live in high elevation. If you live in high elevation, then the atmospheric pressure is lower because you don't have as heavy of a blanket above you. And so if you live at high elevation, the water boils at a colder temperature. So if it boils at 90 degrees versus 100 degrees, it's going to take twice as long to cook. And so high altitude cooking directions are just longer cook times. Otherwise, it's not going to be completely done. And so, so the boiling point does depend on the pressure. And this is called the vapor pressure curve of water. The vapor pressure curve, there are different things we could do. Normally what we do is we don't represent this as a curve. Normally we represent this as a mathematical equation. And then using that mathematical equation, we can just go ahead and calculate temperature at any pressure. Once we fit this, Excel can fit this to an equation. We can use that equation. And so there's different ways. In Chem 4, we use the table, the vapor pressure data table. The vapor pressure data table looks like this. Whole bunch of temperatures, whole bunch of pressures. And then we have the vapor pressure curve. Let's see, well, maybe that's Chem, if we use that. There are 3 ways. In Chem 1A, there's going to be 4 because there's going to be one more equation that we're going to use for vapor pressure. It's a pretty famous equation. But vapor pressure table. The problem with the vapor pressure table is it's a curve. And so if your temperature isn't on right on there, then what we do is we do something called linear interpolation. That is, let's say I'm at a temperature of 63.2 degrees C. Then I'm going to assume it's linear between 63 and 64 and then do a linear interpolation to figure out what my pressure is. So this is a common technique in lab, linear interpolations. Linear interpolations are okay if you have enough data. if you have wide gaps in the data, the linear interpolation is not good because, it's a curve. But if you narrow the gap so the data is very close, that is, you take lots of data, then we can assume that it consists of lots of little straight lines in between the data. And so oftentimes in chemistry, we do linear interpolation with data like this, but that's not the best. The best is just to go ahead and map this out as a curve and then fit it to an equation and then use the equation to do it, which we don't do with Chem 1A. We do that, we do have this instead. What is that other thing? So that's the table. The other option is to graph the curve. So we graph the curve and then just do it graphically. Just draw lines, boom, boom, wherever we want. That's probably better than the linear interpolation data tables. And the final one is just the equation. You just fit that curve to a mathematical equation, and we get the vapor pressure equation, which is given in. There are different forms of this equation. This form here is a very famous equation in Chem 1A called the Clausius-Clapeyron equation. We use this equation. But there are other equations as well. This one's for very specific. This is the Clausius-Clapeyron equation. That's what you can, this is the difference between Chem 4 and Chem 1A. Chem 1A is the same stuff, just you go into it in more detail. Let's see.
So going back to the boiling of water, what does that do with the intermolecular forces
The intermolecular forces,
when it's boiling?
when it's boiling,
Like, will it have what I mean, a stronger intermolecular force?
No. The intermolecular forces are the same here. It's just boiling is a process where the vapor pressure is equal to the atmospheric pressure. When these two are equal, then it boils. And so the intermolecular forces are all the same. The intermolecular forces for water, it takes a lot of temperature to vaporize it. This is why the vapor pressure is low at low temperature, because the intermolecular forces are strong. And so the intermolecular forces are the same. The a typical bond is, what was it, 400. A typical covalent bond is 400 kilojoules per mole of bonds to break. For hydrogen bonding, it's around 25 kilojoules per mole. And so it's significantly less, and it stays at 25. It doesn't change. It's just how much vapor do you have? And is that enough to match the atmospheric pressure? The intermolecular forces are all the same. This curve is based on intermolecular forces there. The way you should think about intermolecular forces and boiling point is you should think in terms of this. We don't compare water at different pressures. We compare intermolecular forces in this way. Which of these three have the strongest intermolecular forces? Pentane, tetrachloromethane, or carbon tetrachloride, or water? Which of these three have the strongest intermolecular force?
Okay.
No.
Water.
Water. Why? Because one, it has the highest boiling point. Okay, the normal boiling point of water is 100. The normal boiling point of tetrachloromethane is 76.5 degrees C. The normal boiling point for pentane is 36.1. Two, it has a higher vapor pressure. Pentane. Water has a lower vapor pressure. Therefore, lower vapor pressure means stronger intermolecular forces. They're more sticky. You can tell the vapor pressure is much. Look at 20 degrees C. What is the vapor pressure of pentane? It's way higher than the vapor pressure of water. You see that? This is the way you would use it. You wouldn't use it just based on this. Otherwise, the intermolecular forces are all the same here. It's water. You'd use it like that.
So warm water has the lowest vapor pressure.
Yeah, this is very common. This curve is very common in Chem 4, Chem 1A. This curve. Here, this is probably more common. Diethyl ether and ethyl alcohol have the same formula. You know, these are called isomers. They have the same formula, but they're, well, actually, no, dimethyl ether. They have quite a bit different properties. Look at ethylene glycol. You know what? Do you recall what ethylene glycol is? Ethylene glycol is used as what?
Is that antifreeze?
Antifreeze. Yeah. Ethylene glycol has those two alcohol groups that sandwich the ethylene group. And so having those two alcohol groups makes the intermolecular forces a lot stronger. You know, because if you look at the structure of ethylene glycol, this is called an ethylene group here, and it's sandwiched with two alcohols. So you have two hydrogen bonding groups on the end, even though this the middle part is not. You know, but look at the vapor pressure, it's way low. The boiling point must be way up there, right? We'd have to extrapolate this out to get the boiling point. We predict it to be way up there. You'd expect ethylene glycol to have very strong hydrogen bonding interactions because we have two hydrogen bonds per ethylene glycol molecule.
Why is the particle system of an engine need to have to be under pressure if the ethylene glycol already has such a high performance?
Because we didn't do any calculations for this, but
Because I know they do have pressureless cooling, but it's not a typical thing.
because of this, this is K sub B. K sub B is the boiling point elevation constant. The boiling point elevation constant for water is only like about 0.5, 0.51, 0.52 degrees C per mole. And so what that means is that if you have, let's say, 1 mole, then your boiling point is only half a degree C higher. So rather than boiling at 100, you can boil at 100.5. 1 mole is 1 mole in a kilogram. A kilogram is about a liter, so that's about 1 mole per liter. And if you go to 2 molar, it's only 1 degree C higher. So you'd have to go to like 10 molar. If you go to 10 molar, then or 10 molal, then you'd be 5 degrees C higher. Well, 5 degrees C higher is not high enough. So you use a combination of high pressure because you want the boiling point to go way higher.
21 psi.
At 21 psi? Yeah, okay, at 21 psi. So it's a combination.
10.5 degrees above normal.
Well, it depends on how much ethylene. You put lots of ethylene glycol in there, for one, and then you have high pressure. So it's a combination of two things to raise the boiling point as high as possible. Because the worst thing is if it starts to boil. If your cooling system starts to boil, then there's no heat transfer because if you have gases have very poor heat transfer and your engine can be destroyed because the temperature can go extremely high. So it's to provide extra safety margin. The other thing is, when I told you when I went to get my car serviced, they just put plain water, tap water, into my windshield wiper. It's going to freeze. You know, when I go up to the mountains, it's going to freeze and when the temperature drops. So I complained about that. But they also just put regular water into my cooling system. You know, and so that's. And a lot of people do that. You go. It used to be like on the Cajon Pass or going up to, through the pass. You see cars pulled over and people putting water in the cooling system. Some people going to the creek and getting water from the creek and then putting it into the cooling system, right? And so it's like, yeah, you want not everybody's gonna put coolant in there because coolant's expensive. A lot of people are just gonna put water in there. It's a lot cheaper. And so I think I'd rather have high pressure and coolant, you know. And then the amount of coolant is a lot. You have to have a lot of coolant in order to raise the temperature high enough. Freezing point's more significant. Freezing point is not the same. It's not 0.5. It's almost 2 degrees C per mole. So you can drop the freezing point a lot lower. Like this is like salt. I use salt water to make ice cream and that kind of stuff because you can get sub-zero temperatures. Temperatures below zero and freeze things faster. Those are colligative properties. The colligative property, all you need to know is boiling point elevation, you know, and freezing point depression. Boiling points higher, freezing points lower. We aren't going to do any calculations. Calculations are so simple.
Speaking of salts, I actually have a steamer, you know, like the steam clothes, and it says the recommended solution is water and salt inside the steamer.
Oh,
That didn't make sense to me.
well, you know, a lot of people say you put a pinch of salt in your pasta, boiling water for the pasta. And a lot of people are saying it's going to increase the boiling point. But when you calculate the molality of that, it's so small. Yeah, it increases the boiling point by about 0.01 degrees C. You know, how much is that going to help in speeding up the cooking? Negligible. So some people did some studies and they said, well, it's for the taste. You know, people like salty foods. They put salt in the water to make the pasta saltier or something.
Yeah, like I said, it just doesn't make sense to me because at first I thought, oh, well, my clothes are going to be smelling like salt, you know, but
There could be other reasons for the salt, you know, to prevent mold or, you know, other things, you know, from forming. Or
dry clean, I guess.
yeah, there are other problems with salt because you get salt buildup and salt can lead to corrosion and other things. Okay, other questions? Ethylene glycol, there was a thing about this. I think they changed it from ethylene glycol because a lot of people are dumping this down the sewer or, you know, dumping it into the stream and it's washing into the creeks and the ocean. And ethylene glycol,
I have a homework question when you're done.
okay. For marine toxicity, they're talking about replacing ethylene glycol with less toxic ones in case somebody decides to dump their antifreeze down the drain, a street drain or something like that, have a lessened impact on it. And so they might have changed the number of carbon atoms in there. I think they use methylene glycol, which is less toxic. Methylene would be 1, or propylene glycol, which would be 3 carbon atoms. Ethylene glycol antifreeze, fluorescent urine, calcium oxalate crystals, propylene glycol. Yeah, actually, none of these sound very good. Yeah, so I was looking at antifreezes and I saw an alternate to ethylene glycol. I can't remember what it was. I looked it up at one time, but now I completely forgot. All right, go ahead, Kate. What was the question?
Oh, chapter 16, 102, there wasn't an answer for that, and just looks like I didn't understand what the ask was.
This is the one I asked you guys to do.
You did?
Yeah.
No.
In, I don't, well, actually, James, I'm not sure. It was one of the classes, maybe the other one. Lily, you got this one, huh?
I'm looking for it right now. I don't actually see it. Homework. I might have it in my notes. We did it last week.
Right. This one's important. The reason I'd like to sign the ones with the answers there. But number 102, the reason I like this one is because this is the Chem 1A titration. The Chem 1A titration that you do is you weigh out some solid. This is a white solid. And it's oxalic acid, which there are a lot of solid acids, organic acids like this. They have, it's a solid because it has very strong, what?
Strong intermolecular forces.
Yeah, strong intermolecular forces. And so oxalic acid has very strong intermolecular forces. The oxalic acids, intermolecular, when we look at the structure, what are the intermolecular forces that you find in oxalic acid? List them for me. Hydrogen bonds.
Carbon?
Is there intermolecular force?
No. Hydrogen and oxygen bonding.
We don't. Hydrogen and oxygen bonding that would be a covalent bond. Intermolecular force. What are the intermolecular? We only have 3 that we talk about in Chem 4. What are the 3 intermolecular forces we talk about in Chem 4? Dipole, instantaneous dipole, and okay. Now list which of those are found in oxalic acid. Right off, you see hydrogen bonding. This is like ethylene glycol. It's going to have strong hydrogen bonding interactions. But ethylene glycol is a liquid, not a solid. So this has even stronger intermolecular attractions than ethylene glycol. And so what are they?
Dipole?
It would be dipole. Where do the dipole interactions come from?
Oxygen.
Yeah, the carbon-oxygen. In organic chemistry, we call this a carbonyl group. So we have the dipole from the carbonyl group and the carbon-oxygen double bond. We have the hydrogen bonding from this. This is called the hydroxyl group. This is called the carboxyl group, carboxylic acid. And so there's going to be hydrogen bonding and dipole from the carboxyl group. These are things you'll have to memorize later on. Organic, if you're going to go that route. And so we have hydrogen bond, we have dipole. Is that it?
There's always instantaneous.
Yeah, there's always instantaneous for everything. Now, when we look at the solid, this is a crystalline solid. And in the crystal of this stuff, we have these oxalic acid molecules. Just something like that. Oxalic acid molecules packed together in an orderly fashion. But this is oxalic acid, 2 waters, and it's a solid. And so what happens is in the crystal lattice, waters get stuck in them. They get stuck into what we call void spaces in the lattice. This is also something from Chem 1A. I mean, we look at crystal structures. And so you'll have water stuck in here. And so what this says is for every oxalic acid molecule, there are 2 waters. So for every oxalic acid, there should be 2 waters. So for every oxalic, I have 2 waters stuck in here. We have different hydrates. This would be the max for oxalic acid. This is completely hydrated. It is possible to dehydrate this by heating it up. If you heat it up, then the waters will vaporize out of there. It'll get too hot for the waters to stay. The waters will leave. But the thing is, when we get the molar mass of this has to be the dihydrate. That is, the waters are stuck. When you weigh this, the waters are stuck in there. It's not, normally void space is empty, but this void space is not empty. This void space is filled with these water molecules and they're going to weigh something. This is an important problem. So when we look at it, I don't want to, actually we could calculate this. Like I said, there are certain ones that you memorize. The common ones that we memorize are hydrogen. So how many hydrogens total do I have? 2 plus 2 times 2 is 4. So altogether, 6 hydrogens. It's going to be 606. Because each hydrogen is 101. And then how many carbons? 2 carbons. That's going to be 2402 because each carbon is 1201. And then how many oxygens? 6 oxygens. So 2 oxygens is 32 times 3 will be 96. And so if you have some of these memorized, then you can do these calculations quickly. And speed is important in timed exams. So especially if you're in organic chemistry and you're doing a stoichiometry calculation, you need speed to do this. You don't want to be fiddling around with a molar mass. It's a simple calculation. It shouldn't take time. Probably. So this is 30, and this is going to be what, 126.08, right? Okay. So maybe I'll just do this one for you. Oxalic acid dihydrate is what we call a primary standard. Do you recall what a primary standard is? This is more important for lab. You don't have to know this definition, but there are 2 categories of analytical standards: primary standards and secondary standards. And in fact, there's a government agency that's funded by billions of dollars called NIST, which stands for National Institute of Standards. Well, anyway, primary standard is a reagent that we can use to dispense an accurately known amount of analyte. And so the easiest way to dispense things accurately is not by volume. The easiest way to dispense it is by mass. So rather than measuring out how many milliliters of acid solution we put in there, we weigh the acid, and then we know how much acid's in there. And so a primary standard has to have a reliable weighing form. The reliable weighing form has to be stable. And so this is why we use the dihydrate. Because if we use the anhydrous form, it's not a reliable weighing form. Because if we use the anhydrous means no water, what happens is the weight is going to increase. So if I put anhydrous oxalic acid on the balance, it's going to suck water out of the air, and it's going to get heavier with time. eventually the weight will stop increasing, but that's not a reliable weighing form. And so the most reliable weighing form for this would be the dihydrate, because this is not going to suck any water out of the air. You know, things that suck water out of the air are called desiccants. They're totally dry, desiccated. And what happens is, if there's any humidity, then they'll get sucked into it.
What was the spacing called again?
So
Between the water and the solid? Voids.
in Chem 1A, you learn about different kinds of void spaces. We have tetrahedral voids. We have octahedral voids. We have cubic voids. So we have different kinds of void spaces. But in Chem 4, you don't even need to know about void spaces or whatnot. You don't care about that. So in your titration, what you do is you measure out a volume of acid solution, HCl. In Chem 1A, in this titration, we're just going to weigh out some oxalic acid dihydrate, 0.750 grams. And so here we put in 0.750 grams of oxalic acid dihydrate, solid. And then what we'll do is we'll add water to this, H2O liquid. And oxalic acid is soluble in water. We expect it to be soluble. Oxalic acid is hydrogen bonding, water is hydrogen bonding. This should be very soluble in water. And so what we end up with is we end up with an oxalic acid solution. Now here, we don't care what the molarity of this solution is. We do know how many moles of oxalic acid there is in here. And so we end up with oxalic acid. If we cared about the molarity, then we'd be very careful how much we add. But what happens is the water is going to dissolve the crystals. When the water dissolves the crystals, what happens to the void space? It disappears and the waters are free. You know, here the waters were imprisoned in the crystal. And then when you dissolve the crystal, all the molecules break apart, and then by freeing all the water. Well, all the waters that were trapped in the crystal can now join all the waters that are free in the solution. And so we end up with oxalic acid aqueous, not oxalic acid dihydrate aqueous. Yeah. And then we're going to titrate it here with sodium hydroxide. 28.0 milliliters of sodium hydroxide. Now this is wrong. Chem 4 is wrong because Chem 4 is only 3 sig figs. In Chem 1A, 3 sig figs is not good enough. We need 4 sig figs. And so they're reading the burette wrong. If you're going to spend $200 on a burette and you only get 1 decimal place of precision, then it's not even worth it. You know, we need 2 decimal places of precision. And so I think this is why so many people in Chem 1A screw it up. Because none of the Chem 4, they're so used to it. They're so used to only 1 decimal place that it's not good enough. But anyway, it's 28.0 milliliters of sodium hydroxide. But the problem is this is an unknown molarity. Here we don't care what the molarity is because I know exactly how many moles of oxalic acid I have in here based on how many grams I put in here. Here, though, I want to know the molarity. So this is called standardizing sodium hydroxide. You do a 2-part titration in Chem 1A. Day 1 is you standardize the sodium hydroxide, which is figure out what the heck the molarity of the sodium hydroxide is. Day 2, you use the standardized sodium hydroxide. Now that we know the concentration of this, we're going to use that to titrate an unknown acid. That's what we do. And then we can identify what that unknown acid is. And identification of the unknown acid is worth a lot of points. Because if you get the acid wrong, then you can end up losing a lot of points. And we identify the unknown acid by determining its molar mass. Because it's a solid acid, we can weigh how many grams we put in there. And once we weigh how many grams, then we can figure out how many moles we have of that acid. If we know if it's monoprotic or diprotic, so they have to give you a little bit. It's not 100% unknown, it's 50% unknown, because they're going to have to tell you if it's a monoprotic, diprotic, or triprotic acid. And so it's not really a great experiment in that sense. You know, it'd be much better if it was a real, true unknown. And so that's limitation. Well, anyway, we want the molarity of the sodium hydroxide. So in order to get the molarity of the sodium hydroxide, we need the moles of sodium hydroxide, and then we need the liters of sodium hydroxide solution. The liters of sodium hydroxide solution is easy, because we just convert 28 milliliters into liters. And so this is the moles of sodium hydroxide divided by 0.0280 liters of sodium hydroxide solution. That's how much solution we use for this. Now, how do we get the moles of sodium hydroxide? The moles of sodium hydroxide is just going to come from stoichiometry. So 0.750 grams. 0.750 grams of oxalic acid dihydrate. And then the molar mass is 126.08. So 1 mole of oxalic acid dihydrate weighs 126.08 grams. And then for every mole of the dihydrate that dissolves, we free 1 mole of oxalic acid molecules. So this conversion factor just comes from the formula. So we get 1 mole of oxalic acid for every 1 mole of oxalic acid dihydrate that dissolves. So let me continue it down here. And then for every mole of oxalic acid dihydrate, gives oxalic acid. Oxalic acid is just H2C2O4. And this is diprotic, so we need 2 sodium hydroxides. This is just a double replacement reaction. And this is going to form 2 waters plus sodium oxalate. Here. And so it's a 2-to-1 mole ratio. We need 2 moles of sodium hydroxide to neutralize 1 mole of oxalic acid. And that's going to give us moles of sodium hydroxide. Once we have moles of sodium hydroxide, we plug it into this equation here, and then we can calculate the molarity. And so I'm going to take 0.75 divided by 126.08 times 1 divided by 1 times 2 divided by 1. So I'll just do times 2. 0.0118971 moles. I'm just leaving all the digits in my calculator, and then I'm going to plug it in up here. So divided by 0.028, I get a molarity 4.424. I'm allowed 3 sig figs, so I'll just carry the 9 molar, or 0.425 molar sodium hydroxide. NaOH. Sodium hydroxide. Then you double check the calculation. Is that what you got?
Yeah.
Okay. So the answer's not there, but this is a standard Chem 1A titration problem that we have here. So that's why this one is pretty important. Number 102. Pretty important. Yeah, that's a good idea.
My last question was for chapter 16.
All right.
Yeah, so number 95, I was kind of confused why they would use bar as an atmospheric pressure.
How many milliliters, 1.50 molar sodium hydroxide solution must react with aluminum to yield 2.00 liters of hydrogen measured at 22 degrees C and 789 torr. What do you mean by bar?
Yeah, so when they do the dimensional analysis, they have 789 torr over 1 bar times 1.013 bar over 760 torr.
Um, I don't know because that's very strange.
Yeah.
That's a very strange way to do it. It's a very strange way to do it because we already know it's 760 torr per atmosphere. Is that mine? No, it's yours. You could do it by bar, but there's no need to do it by bar. Because do you have R memorized in terms of bar, or do you have R memorized in terms of atmosphere? So there's no reason to go to bar. If you had R memorized in terms of bar, then I would. And so I wouldn't. I don't know why I did that.
Yeah, it was just like interesting because throughout the month, we were pretty much using atmospheres as conversions, and then they just throw that one.
Yeah, well, that one is a waste of time. What they're doing is just going in a circle. And it's a waste. I mean, I could do this problem. You want me to do this? How many milliliters of 1.5 molar sodium hydroxide? Must react with aluminum. All right, so this reaction, when you look, what kind of reaction is this? This is aluminum, 2 aluminum plus 6 sodium hydroxides. This is going to yield this 2Na3AlO3 plus 3H2. This is a redox reaction. And so this is aluminum solid. You don't have to worry about predicting this kind of redox reaction. Assume complete conversion. In stoichiometry, we always assume complete conversion. That is, this reaction has a driving force, and this driving force is significant. And so when we assume complete conversion, we assume that 100% of this reacts. So everything falls down. And when we assume complete conversion, the products are so far down here that we don't expect much reverse reaction to occur. You know, that is, one of the complications for some reactions is that even though it's, let's say it's downhill, it's not so far downhill that when we look at the Maxwell-Boltzmann distribution, there is a population that can reverse back up the hill. Sometimes that population that can reverse back up the hill is significant. So we have two types of stoichiometry. We have the stoichiometry that we've been doing for everything. The type of stoichiometry that we've been doing for everything assumes that we have either complete reaction or no reaction. No reaction, the hill is too steep to climb that even when you look at the population, there's nobody in the population that can make it to the top of the hill, essentially. And so when we're doing our stoichiometry, we either predict no reaction or 100% reaction. 100% reaction would be based on the limiting reagent, and that limiting reagent is going to tell us, how much. And so, in other words, if aluminum is a limiting reagent, we expect all of it to react. None of it to be left over. Or if sodium hydroxide is a limiting reagent, we expect all of it to react. None of it will be left over. In chapter 18, we have a complication. In chapter 18, we have the problem where it's not so far downhill that when we look at the population down here, a significant amount can make it back up. If a significant amount can make it back up, then what's going to happen is not all the aluminum is going to disappear. So if aluminum is our limiting reagent, not all of it reacts. Not all of it reacts means if that's our limiting reagent, we're going to get less than 100% yield. So some reactions will have this natural, what we call equilibrium occur. This natural equilibrium means we don't get 100% yield. We get something less. And what we can do is we can do equilibrium stoichiometry. When we do equilibrium stoichiometry, we figure out how much is left over. And that amount that's going to be left over is because we have this natural back and forth. Does that make sense? And so equilibrium stoichiometry is a big topic in Chem 1B. In Chem 1B, you spend most of the semester talking about how to do stoichiometry for these reactions that end up not going all the way down, some go back up, this kind of thing. Or if it's uphill, only part of the population makes it up the hill. How much of that population makes it up the hill? We want to know. And so that's called equilibrium stoichiometry. That's the topic of chapter 18. Chapter 18, we don't do that many calculations because I figure I would do more if there wasn't a gap. I'd do the equilibrium calculations, but what I'm sure is going to happen is between Chem 4 and Chem 1B, everybody's going to forget everything. And so I have to start all over again in Chem 1B. Because you don't do any equilibrium calculations in Chem 1A.
I won't forget.
But if you guys remember it, then it would be useful to know because then you aren't hit with it in Chem 1B, starting from step 1. So let's start from like Chem 4 level in Chem 1B. Well, anyway, we assume that must react with aluminum. And so aluminum is going to be, actually this is going to be stoichiometric. We're going to need to react all the aluminum. And so we need to know how much aluminum there is. Or actually, how much aluminum. We don't need to know how much aluminum. We need to know how much hydrogen is being produced. So over here, we want to end up with 2.00 liters of hydrogen gas. And then we need to go to moles of hydrogen gas here. Then from moles of hydrogen gas, we're going to go to moles of the sodium hydroxide. And from moles of sodium hydroxide, we're going to go to liters of sodium hydroxide solution. Okay. So the thing I'm going to calculate is molar volume here. So what is the molar volume of hydrogen? Well, the molar volume, do you have this equation memorized or can you derive the equation? For the molar volume, I have it memorized, RT over P, or you can derive it or you can do one of the other things.
That's yours.
We can always check this to make sure that the units work out. So R is 0.08206 liters times atmosphere over mole Kelvin. T is going to be temperature in Kelvin. It's 22 degrees C is going to be 295 Kelvin. So Kelvin cancels. P is going to be in torr. So that's 789 torr. And then we only need one conversion factor here. This conversion factor, most people have memorized. But there's 760 torr exactly in 1 atmosphere. The torr is a millimeter of mercury. And so the atmosphere is canceled, and that leaves us with liters per mole. Liters per mole is what we want here for the molar volume. If you don't want to remember the molar volume, then what's the alternate way of calculating the moles of hydrogen? So let me go ahead and calculate this. 0.08206 times 295 divided by 789 times 760. 23.31. We're only allowed 3 figs for this. So 23.3 liters per mole. We can carry one actually. What's the alternative? The alternative is to use the ideal gas law. And so if we want the moles of hydrogen is equal to the pressure of the hydrogen times the volume of hydrogen divided by RT, the temperature of hydrogen. And so the alternative is just to calculate it using the ideal gas law, which might be easier. There's fewer things to remember. But doing this stoichiometrically, we'll just get 2.00 liters of hydrogen gas. And the molar volume is 23.3 liters per mole. So 1 mole of gas is 23.3 liters under these conditions. And so liters of hydrogen gas cancel. That gives us moles of hydrogen gas. And then it's a 3 to 6 mole ratio. So 6 moles of sodium hydroxide for every 3 moles of hydrogen. And then they use the molarity, 1.50 molar sodium hydroxide. And so for every liter of sodium hydroxide solution, we have 1.50 moles of pure sodium hydroxide. And then we convert that into milliliters using conversion here. And so I could save all the digits in my calculator. I'm going to have some round off error. So this is going to be 2 divided by 23.3 times 6 divided by 3 divided by 1.5 times 1,000. 114 milliliters of sodium hydroxide solution. So 114 milliliters of sodium hydroxide solution. Reacted with usually what we can do is react it with an excess of aluminum, and then that's going to give us our hydrogen. That way we don't have to measure out the aluminum. We just add an excess in there. All right, does that answer the question?
Yeah, so where I kind of got lost was after you found that right there, you plugged it in, but what is that ideal gas law equation you wrote up there?
Okay, if I did this using the ideal gas law,
Oh, okay, I see.
this is the way we do it here. So the pressure of the hydrogen is 789 torr. And then I don't want it in torr. I'm going to convert that into atmosphere. The volume of the hydrogen is 2.00 liters. R is 0.08206 liters times atmosphere per mole Kelvin. Temperature is 295 Kelvin. And so this was going to give us the number of moles here. 789 divided by 760 times 2 divided by 0.08206 divided by 295. And so I would calculate 0.0857 moles of hydrogen. Then I just use dimensional analysis. I would start off, that would be my starting point, 0.0857 moles of hydrogen. And then convert that to moles of sodium hydroxide. 6 moles of sodium hydroxide for 3 moles of hydrogen. And then convert that into liters of sodium hydroxide solution. A liter of sodium hydroxide solution contains 1.50 moles sodium hydroxide, and then convert that to liters, 1,000 milliliters per liter. And so times 6 divided by 3 divided by 1.5 times 1,000. I screwed up. 0.0857 times 6 divided by 3 divided by 1.5 times 1,000. 114 times 6. So if you don't want to use the molar volume, we could just go ahead and use the ideal gas. Well, there are 2 ways that you could do this gas stoichiometry. One is molar volumes. 2 is just the ideal gas law. You either calculate N or calculate V. Okay, other questions?
I noticed we didn't really cover the free response for the exams, the practice exams. Like, we don't have the answers for those. So I was wondering, like, when can we go ahead and take a look at that?
You want to look at those on Monday?
Yeah, I think that will be fine. I'll just try to get all the.
Yeah, if we look at them on Monday, what I want to do, actually, my goal today was just to finish the new military health, and then that way next week we can review. You know, I'm not sure
Unless
if
you
we're going
want
to make
us
this.
to the answers and we try to figure it out on our own.
I could do. I'd rather have you try it,
Okay.
and then we can cover it. I can cover it now too. But if I cover it now, then for sure next week I'm going to be talking about.
Can we go over to Monday? So
Yeah,
that
Yeah.
we can-
No.
Just like, wait. Okay.
For chapter 17, do you know the definitions? Arrhenius acid is H plus, Arrhenius base is OH minus. Bronsted, you know, acid is a proton donor, base is a proton acceptor. Lewis acid is electron pair acceptor, Lewis base is electron pair donor. This is the basic definition. Conjugate acid base pairs, that's important for things. Relative strength, we have the table. Predicting acid
Arrhenius is H plus and Bronsted as well.
H plus donor.
H plus.
Predicting acid base reactions, we look at that, and then we have the chart method and zigzag thing. This comparison, we don't need to know the comparison. For the water equilibrium, you need to know a little bit about those. We're not doing any combinations. The way that chapter 18 though is done is there are two things for this. For chapter 18 is actually the two topics in here. One is kinetics. Kinetics is in 18.2 and 18.3 and 18.4. 18.2 to 18.4. And kinetics deals with the speed of the reaction. And then there's the other part is equilibrium, which we call thermodynamics. In equilibrium, we want to know the ratio of the products to reactants. So what we have is, this is like, we call partial reaction. The partial reaction comes about by this. Some of the population can make it up the hill. It's not 0%. And so we have partial reaction. That is, some can make it up, but not all the population. And so a lot of the population is stuck down here, but some population can make it up here. And so the bulk of it. Normally we say this is unfavorable. There's no driving force. Driving force, we need to go downhill. We don't go uphill. And so this partial reaction results if this uphill is not too big of a hill to climb. Or we have this scenario. This is downhill, so we expect complete reaction here, but we only get partial reaction here. We only get partial reaction here because what happens is, yes, the entire population can make it down the hill. Everybody. So if you're in a group of bicyclists, you know, here, if you're in a group of bicyclists, the strong bicyclists can make it to the top of the hill. But over here, all the bicyclists can make it down to the bottom of the hill, but some of these bicyclists might get bored and they want to climb back up the hill. And so what happens is some of these bicyclists, and you can't stop them, because when you look at the Maxwell-Boltzmann, they just have too much energy. They have too much energy, they climb back up the hill, and they're going to be the ones that are going in circles, going downhill, up the hill, down the hill, whereas the bulk of the population says they don't want to hassle with that, they're just going to stay at the bottom of the hill. Yes?
So when you're talking about the population, are you talking about like the molecules or the major and minor species? What exactly are you talking about? Like, does that relate to the major and minor species?
Yeah, the major species is here. The minor species are here. Whereas in this scenario, the major species are here, and the minor species are here. That would be it. And so when we talk about weak acids and weak bases, this is the situation here. With weak acids and weak bases, they partially ionize or partially hydrolyze, and so we get partial reaction. In equilibrium, we want to know how much reaction. I don't want to know partial, I want numbers. So if I have a weak acid, acetic acid, how much hydrolyzes? You know, a little bit is not accurate enough. And so what we do in equilibrium is we try to figure out exactly how much that is. And the key to figuring out how much that is something called equilibrium constant. There are some famous equilibrium constants. One of the famous equilibrium constants is Kw. Kw is equal to the hydrogen ion concentration times the hydroxide ion concentration. And this is a constant. This is 1.0 times 10 to the minus 14 at 25 degrees C. So no matter what I do to the concentrations, they're always going to equal. So if the hydrogen ion concentration equals hydroxide, then it's 10 to the minus 7, or pH 7. But if the hydrogen ion concentration goes up, the hydroxide ion concentration goes down. That's something called Le Chatelier's principle. We'll talk about that later. So this is a famous equilibrium constant, but there are equilibrium constants for all these, because what happens is we have a two-way, and once this hits equilibrium, then the rate of those climbing up the hill is the same as the rate going down the hill. And the same thing here. The two rates are equal. So we establish an equilibrium. There's always going to be 4 people at the top, or there's always going to be, 100 people at the top, whatever it is. And so the equilibrium constant allows us to calculate the stoichiometry. We call it equilibrium stoichiometry. So maybe it's 33% minor species, 67% major species. We can use the equilibrium constant to figure that out. But are we going to do that? We're not going to do that. But this is the bulk of chapter 18. Instead, most of the time in chapter 18 is spent on Le Chatelier's principle. Le Chatelier's principle just says this. What if I change the population? Let's say I add more of the major species. If I add more of the major species, what do you expect to happen? So let's say I had a population of 1 million, and if I go to a population of 2 million, what do you think is going to happen? It's more molecules are going to make it to the top, right? And so it shifts right. What if I add more minor species here? If I dump in a whole bunch of minor species, it's going to shift it the opposite. And so what Le Chatelier's is, once we have this equilibrium established, once equilibrium is established, we could perturb the equilibrium and it results in a shift. And so Le Chatelier's is perturbing a system at equilibrium. Well, we'd like to know what that equilibrium is, but we are not really going to get into it, other than knowing the K. The bigger the K, this is proportional. K is proportional to what? K is proportional to the products over the reactants. So if a K is very small, like Kw here, is there much product? No, very little. In Kw reactions, water plus water yields hydronium and hydroxide. This is a very famous reaction. Water plus water yields hydronium and hydroxide. This is very uphill. This is very uphill because hydronium is a powerful acid, hydroxide is a powerful base. Water is very weak, acid and base. And so this is a very steep climb to hill, and it shows it when we look at the K. When we look at the K, the product is very small. The reactant is very big, relatively. So we aren't going to do it, but we'd like to do it. Instead, what we're going to do is we're looking at the Chatelier's. It's already established. So what's going to happen? So let's take water's equilibrium. The minor species here are H plus and OH minus. The major species, there's water. So if I add more H plus, it's going to shift it downhill, that kind of thing, or shift it one way or the other. So let's just take a look. I already looked at some of these, but let's take a look at the shot waves. Yeah, we'll take a break and then we'll look at these. Increasing concentration, increasing pressure, or increasing heat, or decreasing those. And so let's say this is at equilibrium, and we decrease the oxygen. If we decrease the O2, then what's going to happen? It's going to shift to the left to compensate for the missing O2. Over here, what will happen if we increase or decrease the chlorine? If we decrease the chlorine, we're decreasing the reactant. It's going to shift left to compensate. If additional oxygen is pumped in, then it shifts right to compensate. Ammonia is removed, it shifts right. There. So if we take away ammonia, it shifts right to compensate for that. That means if it shifts right, the concentration of the hydrogen will go down. I think I covered some of these already. Yeah. If the concentration of ammonia were reduced, ammonia is a product, we reduce that, it shifts right. COCl2 is added, it shifts right. Reactant. If the volume's enlarged, it favors the side with more moles of gas. So on the left, we have 5 moles of gas. On the right, we have 3 moles of gas. So larger volume is going to favor the side with more moles of gas. So it shifts it to the left if the volume is enlarged. If the volume is suddenly decreased, it's going to shift to the side with fewer moles of gas. So in this case, we have 2 moles of gas on the left and a total of 3 moles of gas on the right. So it shifts it to the left here. If we have the same number of moles, let's say we have 2 moles of gas on the left and 2 moles of gas on the right, then there's no shift. It doesn't favor one side over the other. And so that's what happens in 33. In 33, we have 2 moles of gas on the left and 2 moles of gas on the right. If we reduce the volume, nothing happens because neither side is favored at smaller volume. And so it stays. And then we have heat as well that can impact things. Consider the following system at equilibrium. Here, they give us the K value, which is 10 to the third, so it's kind of big, so it favors the product. If the volume of the equilibrium suddenly increase, so if we increase it, it's going to favor the side with more moles of gas. So on the left, we have 3 moles of gas, on the right, we have 2 moles of gas, so it shifts it left. Which direction will we shift in if it's cool? If it's cold, removing heat. Heat is a product, so if we remove product, it's going to shift it to the right. It's going to make some product to compensate for it. It's got to maintain a balance. And so if we take away product, we've got to make more product to maintain a balance. Here, if the temperature is suddenly increased, we're adding more heat. If we add more heat, if it's too much heat here, it's going to shift it to the right. If your purpose was to increase the yield of sulfur trioxide, would you increase the temperature or decrease the temperature? Here, if my purpose is to increase the amount of sulfur trioxide, I'll decrease the temperature. Because if I decrease the temperature, I'm removing heat. If I remove heat, it's going to shift it to the right to compensate. So that's going to yield more sulfur trioxide and yield more heat to compensate for the lost heat. 38, consider the following system in equilibrium here. If the temperature of the system is suddenly decreased, so this is negative. Delta H in negative means it's exothermic. So that means heat is a product. So if I remove product, it's going to shift to the right. If it shifts to the right, then the concentration of iodine decreases as it shifts to the right. The solubility of calcium hydroxide is low. It reaches about 2.4 times 10 to the minus 2 molar at saturation. In acid solutions with many H plus ions present, calcium hydroxide is quite soluble. Explain this fact in terms of the Chatelier's principle. Calcium hydroxide dissolves in water. When it dissolves in water, it splits up into ions. The soluble, soluble. If we add acid to this, it perturbs this system. And so if I add acid to this, what will it attack? If I add H plus, then what happens is the H plus will attack the hydroxide. In other words, it removes hydroxide. So if I remove hydroxide, then I'm removing product. If I remove product, this is going to shift right. Le Chatelier's principle says we're going to have to shift right to compensate because we have to maintain a balance. And so if we shift it right, then more calcium hydroxide dissolves. So this is using Le Chatelier's principle. Alternatively, this is a metathesis reaction or acid-base reaction. And that is, we have calcium hydroxide solid being attacked by acid, H plus. And that's going to form calcium something, calcium ions, plus 2 ions. And so, for example, if the acid were hydrochloric acid, we'd form calcium chloride. If the acid were nitric acid, we'd form calcium nitrate. If the acid were hydroiodic acid, we'd form calcium iodide. So, this is a metathesis reaction.
The way I look at metathesis is it's like an umbrella term to gas formation, solid formation, and precipitation.
Yeah. Let me just show you some examples of the equilibrium constants. Okay. This you don't need to know. Pure solids and liquids are omitted. Okay. Might it? Anyway, if we have this one, H2O liquid plus H2O liquid, this gives us hydronium and hydroxide. And K is equal to the hydronium ion concentration times the hydroxide ion concentration. This is the famous KW. There's the liquids we ignore. But if it's not, let's say if we had CO gas plus H2O gas yields CO2 gas plus H2 gas, then K is going to equal the CO2 concentration times the H2 concentration divided by the CO concentration and the H2O gas concentration. So here we have the products over reactants. This is the same thing. This is products over reactants, but the reactants are just one in this case. Sometimes we'll have a solid, like in the next here. So number 42 has a solid ammonium hydrogen sulfide. Solid. And this is going to go to ammonia and H2S. Ammonia is a gas, and H2S is a gas. And so K is going to just be the ammonia concentration times the H2S concentration. The solid we omit. It's not really omitted from the equation. It's there as a number one. And so it's a product over reactant. And when there's a number there, these are, so if there's a number, what we do is we square it. So let's just take a look at one more. The one more will be zinc phosphate. Solid goes to zinc 2 plus, 3 zinc 2 plus, and 2 phosphate. This will be the equilibrium here. And the equilibrium constant will be zinc. Okay, now what we do with this 3 is we cube it. So we end up cubing the zinc concentration, and we end up squaring the phosphate concentration. That's what happens. And so it looks a bit different. And then zinc phosphate is pure solid. And so that's you aren't going to have to derive any of these. These are just showing it. And then there's a number for this. This is a constant. This is a very famous number called KW. In Chem 1B, everybody memorizes this number, 1.0 times 10 to the minus 14. This is a constant. I don't know what the number is for this, but there's a number for this. This is a constant here. Once we have the number, then we can do calculations. So, for example, if we know the number for this, we can do things like pH calculations, and POH calculations, and hydronium concentration calculations, and hydroxide concentration calculations. So once we get the number, then we can do lots of things. And so this is why we want the numbers for these. There's going to be a number. You can look it up. Usually it's given in some kind of table or something. And then once we have the number, then we can do all kinds of calculations. And all kinds of calculations is we can figure out what the ratio is and other things. But before getting to the calculations, we would like to know the significance of this ratio. So for example, here, if I look at this reaction, which is silver and cyanide, this forms this is a complex anion. This is called dicyanoargentate ion, argentate 1. And so it's a very funny looking species. This is an example of a Lewis acid-base reaction. Silver ion is electron pair acceptor, that's the acid. Cyanide is the base. And this Lewis acid-base reaction formed the Lewis acid-base adduct, which is this species here. But if we look at the equilibrium, the product over reactant is 5.6 times 10 to the 18. 10 to the 18 means this is all product or all reactant. It's a huge number, 10 to the 18. It's all product. Huge numbers, products, They're heavily favored. 10 to the 18 is a huge number. 10 to the minus 5, small number, which means it favors reactant.
Is the dihydrogen sulfide, is that a gas or solid?
It's a gas. Okay. Hydrogen sulfide. That's a common name. And so we want to know these numbers here, and then we can do all the calculations for this kind of stuff. And so these are equilibrium calculations here, which is optional. I'm going to skip all the equilibrium calculations. Oops. And you can skip them too, but what we do is we set up something called, let me just briefly say this.
Don't erase those Z.
We set up something called an ice table. Pure solids and pure liquids we omit. And so we set up an ice table like this. ICE stands for initial, C stands for change, E stands for equilibrium. And so if we start off at 0 and 0, let's say no water molecules have collided. And so there's no hydronium and hydroxide. And then we want to figure out how much hydronium and hydroxide are formed. So we call it plus X because we're going to form the same amount. So we end up with X molar here and X molar here. Then we take the K value here. Kw is equal to the hydronium ion concentration times the hydroxide ion concentration, and that's equal to 1.0 times 10 to the minus 14. And so this hydronium concentration is going to be at equilibrium, and the hydroxide ion concentration is at equilibrium. So the equilibrium hydronium concentration is X, and the equilibrium hydroxide concentration is X. And so this is equal to X squared. X squared is equal to 1.0 times 10 to the minus 14. Therefore, X is equal to 1.0 times 10 to the minus 7. And therefore, X is equal to 1.0 times 10 to the minus 7 molar. And this is pH 7. And this is also equal to 1.0 times 10 to the minus 7. So this is an example of a equilibrium calculation. In this type of stoichiometry, we set up an ICE table here to figure out how much actually makes it up the hill. How much makes it up the hill? If we start off with everybody at the bottom of the hill, this is how much makes it to the top of the hill. How much makes it to the top of the hill is based on the K. This K is a very steep hill decline. And so most of the population, the water molecules are going to be down here, just about 4. So the actual K expression, you're not going to have to do. All you have to know is it's a product of reactant ratio, but a little bit more complicated. Equilibrium calculations, you don't really know. And so this goes into a whole bunch of equilibrium calculations. But all the equilibrium calculations are set up the same way. We set up an ICE table like this. And then we try to figure out the ratio. If it's not a pure liquid or pure solid, then we factor that into the ICE table. All right, this is chapter 18. Chapter 18 deals with the kinetics. The speed, of the reaction is going to depend on the Maxwell-Boltzmann. This is thermodynamics. Thermodynamics tells us, the equilibrium. Kinetics tells us how fast. And so from kinetics, we look at the reaction profile. Reaction profile, the activation energy, this would be an endothermic reaction, or or it could be an exothermic reaction. In an exothermic reaction, we have a profile like this. So this is downhill, but it might go slow. This might go slow because initially we have to climb up the hill. And this is the activation energy here. And this is delta E here. Delta E is exothermic. Here the activation energy is quite a bit bigger. And delta E is not favorable either. Delta E here is endothermic. But the activation energy is going to dictate how fast this reaction occurs. And that's going to depend on the temperature, in the population. And also the pathway. If we have a catalyst, remember catalysts provide an alternate hill for pathway, so maybe it goes around rather than over the top. And so those are the types of things. Things that speed up the reaction will be temperature, catalysts, that kind of stuff. We looked at that too in chapter 18. Chapter 19, we talked about a lot of chapter 19 already. And so for chapter 19, I just want to focus on voltaic and electrolytic cell. Batteries and electrolytic cell are using electricity to power reactions, electrolysis reactions. We already did oxidation numbers. We already did oxidizing agents and reducing agents. We already did strengths of oxidizing agents and reducing agents. We already predicted redox reactions using the chart method. Inventory, identify the oxidizers, reducers. And there's a comparison between redox and acid-base reactions. Skip that. And so I'm going to talk about batteries and then skeleton redox. Skeleton redox, it says optional here, but I'm going to do it. It's 19A. This is important for Chem 1A. And so we'll talk about batteries and skeleton redox. So basically section, although for batteries we need to know reactions as well, oxidizing agents, reducing agents. So this is essentially section 19.2 and 19.8. So we've already done the other sections. So this is why I kind of wanted to wrap up the new stuff today. And so then we can review the other stuff and redox if we want. And so 19, your sections are going to be different. So I'm just going to call this electrochemical cells. We have two types of electrochemical cells. We have what are called the spontaneous cells. The spontaneous cells just operate spontaneously. They don't need anything to drive them. And the spontaneous cells are the voltaic. Voltaic cell is the same thing as a galvanic cell. And so here we have voltaic and galvanic cells. And then we have these ones that are non-spontaneous. The non-spontaneous ones must be forced. And so here, these are forced reactions using electricity. And so basically, the spontaneous ones, these are downhill reactions. And the non-spontaneous ones, these are uphill in terms of energy, in terms of thermodynamics. Uphill, downhill. And so let's first look at voltaic cells or galvanic cells. Voltaic cells, we use redox to generate electricity. So let's look at a typical redox reaction. So if we have solid zinc and copper 2 sulfate, what forms here?
Zinc sulfate and copper solid.
Zinc sulfate and copper solid. This is the CE. What's the IE for this?
Zinc solid plus copper 2 plus and sulfate yields, is that going to be zinc plus 2 sulfate plus copper sulfate?
Okay, what's the NIE?
The zinc solid yields zinc 2 plus and copper solid.
Is that balanced?
No, you need to add 2 to the zinc solid.
Add a 2 to the zinc solid. Now is it balanced?
You're missing the.
Yeah.
Plus copper 2, excuse me.
Let me redo this. So we're going to have zinc solid plus copper 2 ion yield
This is zinc 2 plus copper solid.
plus copper solid. There we go. Okay. So what happens here? This is what we call the redox. And what we can do is we can divide this redox into half reactions. So 1/2 reaction here is going to be zinc goes to Zn2 plus 2 electrons. And so the zinc atom lost 2 electrons here and going to zinc 2 plus. The other half reaction would be copper 2 plus, then gain those 2 electrons to form copper metal. So in other words, 2 electrons were transferred from the zinc to the copper ion in this redox. We have certain names for these things. So, for example, is zinc the oxidizing agent or is zinc the reducing agent? You remember, does the oxidizer take electrons or does the oxidizer lose electrons?
Take.
Oxidizer takes electrons. And so that means copper must be the oxidizing agent because it's taking 2 electrons. And therefore, the loser is the reducing agent. Now, there's something called oil rig. Have you heard oil rig? Oil stands for oxidation is loss of electrons. Is that? I thought I had turned that off. Rig is reduction is gain. And so this one, the reducing agent undergoes oxidation. You know, the oxidizing agent oxidizes the reducing agent. And therefore the reducing agent undergoes oxidation. Oxidation is lost. So we call this first one the oxidation half reaction. If we look at the second one, the copper 2 oxidized something, therefore it's reduced in the process. Reduction is gain. So this is called the reduction half reaction. And so we have the oxidation half reaction, which is loss, and the reduction half reaction, which is gain. And if we add both the half reactions, we get the redox. The redox is reduction and oxidation. In a voltaic cell, what we do is we separate the oxidizer from the reducer. So what we do here is we'll put the oxidizer in one beaker and reducer in another beaker. And so, who's the oxidizer? Copper 2. So we want copper 2 to take the electrons. The oxidizer takes the electrons. But if we put the zinc in here, the copper 2 will take the electrons directly from the zinc. And so what we're going to do is we're going to put another beaker over here, and then we'll throw a piece of zinc in here. This is just going to be zinc solid. Yeah, there's solid kind of zinc here. And then we'll throw some water in there. So how can I get my copper 2 to take the electrons from zinc? If I put them in the same beaker, it would work, but what I'm going to do is I'm going to put something called an electrode in here. We have two types of electrodes. We have a reactive electrode, which is this one. This is reactive electrode. And then we have an inert electrode. Inert electrode is this. So what do we use as an inert electrode? Probably the most common inert electrode is platinum metal. Platinum metal is used because platinum is very stable and unreactive. And so if you want one of the most inert metals on the periodic table, it'd be like platinum. What would be another inert metal on the periodic table? Not totally inert, platinum is not 100% inert.
What's the name again?
Inert just means unreactive.
Unreactive.
Lead is pretty reactive. Lead will be reacting with lots of different things. Yeah, they do, but it depends on the battery. In car batteries, they use lead as the electrode, but it's a reactive electrode. And on one side, and on the other side is different. Gold, yeah. Gold is another common electrode. But platinum and gold are really expensive. And so,
You said it doesn't react though, right?
yeah, they don't react, but they're very expensive. In fact, when I think back to when I was at UCSB, we had drawers filled with platinum electrodes. Platinum electrodes, platinum boats. Probably now $1 million. Wow. Almost must be. I wonder what happened.
So when you're talking about reactions, because gold and platinum they conduct electricity.
Yeah, right. They conduct.
I'm a little confused on what you mean by they don't react.
They conduct electricity, but by conducting electricity, for example, if I put zinc in here, the zinc will be eaten away. And so I might start off with zinc, but I end up with zinc in solution. So if I put zinc in here, the copper will be like permanently eaten away. But if I put platinum in here, the copper 2 will try to take the electrons from platinum, but will be unsuccessful. If I put gold in here, the copper 2 will try to take the electrons from gold, but will be unsuccessful. But platinum and gold are too expensive. What's cheaper? What's cheaper would be graphite. Graphite is cheap.
Oh,
The problem with graphite is this. If I use graphite here, right, the copper 2 might take electrons, or try to, but if it were successful in taking electrons, it's going to coat it with copper solid. And so what I'm going to do is I'm going to have copper-plated graphite. If I use platinum, I'd have copper-plated platinum. If I use gold, I'd have copper-plated gold. And so the cheapest one that's going to be good and clean will be copper in this case. And so if I make this out of copper, copper ions getting in a tug of war with copper metal, who's going to win? Copper versus copper, who wins in the tug of war? It's a tie. And so copper will be an inert electrode in this case, because it's copper 2. And so copper 2 is going to try to take the electrons from copper, but it's not going to be successful. But then what I'm going to do is I'm going to have a copper wire here. And this copper wire, I'm going to connect all the way to the zinc here. Now, if you recall, metals, we have the electron sea. Remember? We have a sea of electrons here. And the sea of electron is going to go through the wire too. The sea of electrons. So if there's a tug on the electrons here, it's going to feel it, you know? There's going to be ripples in the sea. The copper 2 is trying to take the electrons. But the sea of electron extends all the way to the zinc, because zinc is a metal too. And zinc being a metal, there's also a sea of electrons here. And so as soon as the electron sea hits zinc, then it should form zinc 2+. So this would be zinc 2+ in air. Zinc 2+ in air is not stable. In air is not stable. Whereas zinc 2+ in water is stable because we can have a hydrated ion. Do you remember hydrated ions? The oxygen in water will orient around zinc 2+ to help stabilize it. And so zinc 2+ aqueous is much better. And so once we hit one of these, then the electrons will be lost by zinc, and then it can go into the ocean of electrons and then be fed to the copper 2. So copper 2 is pulling on the electron sea here, but who's losing the electrons will be zinc over here. So the copper 2 gains 2 electrons. When copper 2 gains the 2 electrons, it's going to plate out copper solid. It's going to plate out here. And so over in this beaker, we're going to have copper 2 plus 2 electrons yields copper metal. Over in this beaker, we're going to have zinc solid goes to zinc 2+ aqueous plus 2 electrons. So it would be aqueous now. And the electrons, do you see the electrons are going to flow from left to right? But there's a problem. Hydrated ions, yes, hydrated ions are more stable. But the problem is water is just delta minus. So it doesn't completely neutralize the charge here. And so what we have here is we have a buildup of positive charge in this beaker. Over here, we're losing the copper 2. As we lose copper 2 and replace it with copper solid, we're losing positive charge. The negative charge is the same because, you know, we have sulfate in here. And sulfate's not doing anything, it's a spectator. And so over here, we're going to have a buildup of negative charge. This is called a space charge. And it equals a voltage. A voltage is when we separate the positive and the negative. And the more we separate the positive and the negative, the higher the voltage. So the greater the positive charge build up here, and the greater the negative charge build up here, the greater the voltage. Pretty soon, that voltage gets too high, and it stops everything. And so the space charge prevents further reaction. So maybe we can have a tiny bit of reaction, but then the static electricity in these two beakers is too high to sustain. And so the reaction stops. And so we need something to eliminate the space charge. What we use to eliminate the space charge is a bridge between the two beakers, like this. This bridge between the two beakers contains the salt, and therefore we call it the salt bridge. The salt bridge is just a solution or a gel or, whatever, like here. It's this tube shown over here. And in this tube, they put the salt, potassium sulfate, in here. You could have any salt in here, but in this, we put potassium sulfate here. So in the salt bridge, for every Zn2 plus that forms, one sulfate ion moves into the solution here in the salt bridge. And it's just a solution. Eventually, everything's going to mix. For every copper 2 plus that's lost here, 2 potassiums move into the beaker here. So the salt bridge maintains electrical neutrality because we lose 2 positive charges to this beaker and we lose 2 negative charges to this beaker. So the salt bridge maintains electrical neutrality, so there's no space voltage, no space charge that builds up here. But what it does is the salt bridge neutralizes the space charge. So if we can neutralize the space charge, then what that means is that the electrons can flow and we generate electricity. And so this is the electricity here. Electricity is just this flow of electrons through the wire. And so if we put a light bulb in there, we can light up the light bulb. Or if we put a voltmeter there, the volts are going to be voltage. Voltage is just the pressure and the force. The higher the voltage, the more force there is in the electron. So high voltage, lots of force. Low voltage, a little bit of force. Passing through. Amp is how many electrons pass through the wire per second. We don't actually measure the number of electrons, we measure the charge. So amp is the number of coulombs. Coulomb is a unit of charge that we use in physics. And so 1 amp is 1 coulomb's worth of charge. 1 coulomb's worth of charge is a ton of electrons. And so one amp is a huge number of electrons passing through in 1 second. Let's say amp. And so here we can measure the voltage here. And in this particular battery, it comes out to 1.1 volts. It's a 1.1 volt. It's well, it's going to depend on the concentration. So over here we have 1 molar concentration of copper 2 plus. We get 1.1 volt. If we go to 6 molar copper 2 plus, the voltage goes up. We just have a higher concentration. If we go to lower concentrations, the voltage goes down. So the voltage is going to depend on the concentration. But this is essentially the basics of a battery here. We have names for these types of things. This is called the anode, this electrode. This is the anode. We usually go anode to this electrode to the cathode. And so A to C. Electrons go left to right. The anode, why do they call this the anode? They call it the anode because the anions in the salt bridge migrate to this beaker. And so the sulfate anions. They call this the cathode because the cations in the salt bridge migrate to this beaker. At the anode, we have oxidation. Oxidation always occurs at the anode. Oxidation, we generate electrons. And so at the anode, we generate the electrons because that's where oxidation occurs. At the cathode, we consume the electrons. That's where reduction occurs. And so this would be the anode half reaction or the oxidation half reaction. This would be the cathode half reaction or the reduction half reaction. And the net redox reaction is just given by the NID here. So you can see oxidation occurs at the anode. We generate electrons here. The zinc is being eaten away. As we form zinc ions, we need sulfate to compensate for that charge. Even though the hydration will help, it doesn't help enough. As we lose copper-2 ions at the cathode reduction occurs, the potassium ions migrate. So we'll need 2 potassiums for every copper-2. It's not balanced. And so the copper-2s pick up the electrons and then deposit copper metal. So you can see copper metal atoms being deposited here. The sulfates here are spectators. Over here you can see the zinc being oxidized. So ions. The sulfates there are just balance the charge. They're potassium ions. They didn't show the potassium ions over here. So this is a basic cell. And all the other cells are going to be similar. There's going to be an anode and a cathode. Anode is where we generate the electrons. The cathode is where we consume it. So the oxidizers at the cathode, producers at the anode. And so lithium batteries, lithium metal is the anode. Lithium is going to generate the electron. The cathode is manganese 4. Manganese 4 is oxide. We use manganese 4 oxide here. And so we transfer the electrons from lithium metal to manganese 4. This is for certain types of lithium batteries. There are other types of lithium batteries too that don't use lithium metal. This is a nickel cadmium battery here. We have 2 basic cells. This cell is called a secondary cell because we could recharge it. How do we recharge this battery? How we recharge this battery is we put a power source here and force the electrons to go backwards. If we force the electrons to go backwards, then we're forcing the reaction to occur using electricity, which is called an electrolytic cell. So we can recharge this battery. It's a secondary battery. So secondary batteries are rechargeable. So this would be a secondary battery. It's rechargeable. This is a secondary battery. But some batteries are not rechargeable. Those are called primary batteries. Primary batteries cannot be recharged. The reaction does not easy to reverse. So here we can this is kind of like recharging the battery here. We put a power supply. The power supply could be another battery and force the electrons to go backwards. That would be recharging the battery. But not only can we recharge the battery using electrolytic cell, we can also generate reactive chemicals using electrolytic cell. So let's take a look at electrolysis and electrolytic cells. So the first thing is we need some power supply to force the electrons to go backwards. And so normally we have electrons go left to right, anode to cathode, A to C. In an electrolytic cell, we have the electrons go backwards. The way we do that is the power supply has a positive terminal. We connect the positive terminal to where this is going to suck the batteries in. And it's going to spit the batteries out of the negative terminal. So it depends on the voltage. The higher the voltage, the greater the positive charge here, and the greater the negative charge here. The lower the voltage. And so let's go with a high voltage here. If we go with a high voltage here, then we're going to oxidize something. And so we oxidize species that's easiest to oxidize. And over here, we're going to reduce the species easiest to reduce? The species that's easiest to oxidize is called the best or the strongest reducing agent. The strongest reducing agent is easiest to oxidize. And the species that's easiest to reduce is the strongest oxidizing agent. Usually we don't want to oxidize the electrodes, so we use inert electrodes for this. And so the typical inert electrode would be platinum. And over here, we don't really want to reduce our electrode over here. So we'll just use platinum here. What they put in here is liquid sodium chloride. So they have sodium chloride liquid, molten sodium chloride. So it's too hard to oxidize platinum. It's easier to oxidize chloride. Chloride would be the strongest oxidizer present in this case. And so what we can do is we can oxidize the chloride here. And so the half reaction here would be 2 chlorides goes to chlorine plus 2 electrons. Chloride's not so easy to oxidize, so we need a high voltage for this. So we crank up the voltage until we can strip the electrons off chloride. When we strip the electrons off chloride, we generate chlorine gas. And so over here, we're going to generate chlorine gas. 2 chlorides come here, generate the chlorine gas, and 2 electrons get fed into the power supply here. Then over here, what wants electrons? Well, the only species that wants electrons over here would be sodium. And so we take 2 sodiums, we'll take 2 electrons from this electrode to make 2 sodium. Now this is going to be very hot, and so the sodium is going to be liquid sodium metal. Liquid sodium metal is less dense, so it's going to float to the top here. And so we're going to get sodium liquid. We don't want sodium liquid to come into contact with chlorine gas. If that happens, there's going to be an explosion. So what we need to do is we need to have the sodium liquid float on the surface of the molten sodium chloride. Then we can remove it. And so the sodium liquid over here, there's got to be a barrier here to prevent them from coming into contact. And so using this method, a molten sodium chloride electrolysis setup, we can make sodium metal, which is super reactive, and chlorine gas, which is super reactive. And so we can make very reactive chemicals using electrolysis, or we can recharge batteries. So there are 2 things that we do with electrolytic cells. One, recharge secondary batteries. Or 2, synthesize unstable chemicals. Actually, 3. People put their baby shoes in here and plate metals on here. So we do electroplating. The 3 common things that are done with electrolytic cells. Are batteries used to power MP3 players best classified as electrolytic, voltaic, or galvanic? Are batteries used to power portable MP3 players best classified as electrolytic, voltaic, or galvanic? Well, the batteries are always voltaic or galvanic. Because batteries generate electricity spontaneously, unless it's dead. Whereas electrolytic, you need a power source to do it. And so the battery would be like a lithium cell. So voltaic and galvanic are the same thing.
Is that why sometimes you can, like, if your car doesn't start, you wait, sometimes it'll, without company, like,
Yeah.
power back.
Yeah, it could. Power back because it's a chemical reaction. So
So a solar battery would be electrolytic?
solar cells.
Yeah. Okay, can you go back
Solar,
to the
solar cells you can use to do electrolysis. For example, here we need a power source. And the power source, if the power source were the sun, then this is an electrolytic cell. Solar cell is generating electricity. If we generate electricity, it would be classified as a voltaic, so it's called photovoltaic cell. So we have a photovoltaic cell here. And this photovoltaic cell might power an electrolytic cell. In fact, that's what people want to do. People want to use a photovoltaic cell to power this electrolytic cell in which we have water. When we oxidize water, remember oxidation occurs over here. So electrons are going this way. And so we're going to have oxidation. When we oxidize water, we're going to take electrons off oxygen. Oxygen has the water. Hydrogen's +1, oxygen's -2. And so when we oxidize water, we generate oxygen gas over here. Okay, so we're going to take water and we're going to generate oxygen gas. And so we'll take 2 waters, we'll generate an oxygen gas plus 4H plus, and then for each oxygen, we'll lose 2 electrons. And so we can actually oxidize liquid water to generate oxygen gas. So we can have oxygen gas form here. Okay, over at this electrode, we're going to have reduction occur. Electrons are going to be forced out this way. And when we crank up the voltage, like if we use a 9-volt battery, something like that, then that will occur. Reduction, hydrogen will gain the electron and will form hydrogen gas. In this process, we also have hydroxide, 2 hydroxides, and we'll have 2 waters. 2 waters, 2 waters, plus 2 electrons. Let's see if that's balanced. So water gains electrons. That gives us 4 hydrogens. 4 hydrogens, 2 oxygens. Nice, nice. We'll generate hydrogen gas here. This is an electrolytic cell. In this electrolytic cell, we're generating hydrogen gas and oxygen gas. And when we add these up, we're going to form twice as much hydrogen as oxygen. Because it's placing 2 electrons here, 4 electrons here. And so I'm going to have to double this one by 2. We have 4 electrons here, 4 electrons here. And so this is called the reduction half reaction. This is the oxidation half reaction. And the net redox reaction, we add these 2 up, making sure the electrons cancel. So we have 4 electrons here. That's going to give us 4 waters here. And 4 waters. Over here I have 2 waters. That's 2 waters. And then I'm going to get 2 hydrogens. 2 hydrogens. Plus 4 hydrogens. Plus the oxygen. Plus 4H plus. And then the electrons cancel. Well, 4 hydroxides plus 4 hydrogens is going to yield 4 waters. And so these 4 waters will cancel out these 4 waters here. And the net redox reaction when 2 H2O liquids goes to 2 hydrogen plus an oxygen gas. This is not a favorable reaction. We can force this reaction to occur using a power supply. And the power supply, hopefully, will be photovoltaics in the future. But right now, it's not. So generating hydrogen is very expensive because we have to use electricity to. Right now, it's too expensive to use. And so people are talking about, right now, the electricity, most electricity is made by burning coal in the US. And it's cheap. And so that's preferred. However, if there are, do you really want to burn lots of coal to make hydrogen, to burn the hydrogen?
So wait, if they're talking about like electric cars, we're still burning coal for that?
Yeah. So when I charge my electric car, it's not carbon zero. There's a lot of CO2 being generated because in California it's mostly methane, and so or mostly methane. In the East Coast it's mostly coal. Also, there's lots of coal in Utah, Idaho, those places. They'll have coal-fired electric power plants. Lake Mead, which is hydroelectric, is generating zero right now. Most of that goes lost, I guess, anyway. And so when you power your electric car, you're actually burning a lot of methane to power your electric car. And so, how green is that? And so people are looking for greener ways of producing electricity. And, right now, it's not quite there. And so a lot of people are pushing the hydrogen economy. So, for example, Toyota, they're not really pushing full electric vehicles. They're pushing hydrogen fuel cells. I can talk about fuel cells. Yeah. Fuel cells are voltaic cells. Okay, so let's look at a hydrogen fuel cell. Hydrogen fuel cell, we have hydrogen gas coming here. Hydrogen gas is going to make 2H plus and then 2 electrons if it's oxidized. What's oxidizing the hydrogen gas? What's oxidizing the hydrogen gas is oxygen gas in air. So the oxygen gas comes over here and plucks 2 electrons. And so 2 electrons will come in here. And this will be half an oxygen. And this is going to make, this is going to make with water. That's water. This is going to make hydroxide. This is not balanced. I should balance that. Plus, actually, I should balance it to make H. Anyway. And so we have this, and then the hydrogen ions and the hydroxide ions combine with each other. And so we're going to generate electricity this way. And so the fuel cell is, the hydrogen comes from your fuel tank. And this is why it's called a fuel cell, because the fuel is contained in a tank, and that tank, as long as you keep filling it with more hydrogen, this battery will just keep going forever, as long as you keep adding hydrogen to your fuel cell. And so the fuel cell has basically the fuel, that is, fuel being the reducer, electron-rich species over here. We can have methane fuel cells as well. Not only can we oxidize hydrogen or burn hydrogen, we can oxidize methane too. So methane fuel cells used to be popular, but right now it's hydrogen, the hydrogen fuel cell. And so Mercedes and Toyota offer fuel cell electric vehicles in which you generate the electricity in the car itself. And so you don't plug it in. The electricity is generated on demand. adding the hydrogen.
Aren't you also expending electricity for energy?
Yeah, that's right. How do you generate the hydrogen? Electrolysis. How do you generate the electricity for the electrolysis? Burning coal, burning methane.
And what about wind, using wind turbines?
You could use wind, but wind's not blowing all the time. And so what do you do when the wind's not blowing? And well, this is what they're saying. The problem in Europe is the problem in Europe is they switch to wind and solar, but in the winter, the wind might be blowing, but the solar they're going to have trouble.
Do they have hydrogen deposits, like, or like if they have gas?
No,
Smaller?
they don't have hydrogen deposits because hydrogen's too reactive. So they don't really have it. There are other ways of making hydrogen, chemically, the water gas shift reaction and others, but those require temperature. Right now, the big thing for hydrogen production is these nuclear reactors, these new type of nuclear reactors. These new type of nuclear reactors are use the helium as the coolant. You know, in a normal nuclear reactor, do you know what they use for coolant? Water. But the problem with water is, what's the boiling point of water? 100 degrees C. So what they use is they use pressurized water. Of course, if there's a leak in the pressurized water, it'll convert to steam, and then you're going to have cooling issues, and you could have potential meltdown. And so they use high pressure liquid water cooling lines. But still, that even high pressure, that's going to limit the temperature. You can only get to a certain temperature because things will start to corrode quickly and become unstable. So they're using alternative coolants to water. Do you know what the alternative coolant is? This was mind blowing because I wouldn't have thought this at all. Not liquid helium.
Antifreeze.
Gaseous helium. Helium cooled nuclear reactor. This is mind blowing because gases are mostly, empty space, right? But the wild thing about this is, well, it's a gas, so the temperature can go much higher. If the temperature, they want the nuclear reactors to operate as high a temperature as possible because the higher the temperature, the more efficiently you can generate electricity. There's a bigger temperature drop. This is in physics. And the thing about helium is helium has, do you know helium's specific heat is greater than that of water? Water specific heat, is a big deal. It's made out of water specific heat, 4.18 joules per gram degree C because it's so hot. But helium specific heat is over 5, which is mind boggling because it's a gas. It's got a high specific heat, which means that it'll work well as a heat absorber, like water. Water is an excellent heat absorber. We use water as a heat reservoir to cool things down. Well, helium can be used as a heat reservoir to cool things down, and then you have these high temperature nuclear reactors. Well, with these high temperature nuclear reactors, they're talking about generating hydrogen gas cheaply, because that's a cheap source of heat. And you need high temperatures to generate hydrogen gas chemically. By the water gas shift, you take water and a steam and carbon monoxide or something like that, and you do different things. And so that's called, they have different names. Have you heard green hydrogen, blue hydrogen, red hydrogen? Have you heard that? It depends on how it's made. I think it's called red hydrogen. Let's see. If my memory is good enough. Oh shit. Android smartphone.
less than 2 stars.
What are the 4 types of hydrogen? Green hydrogen, blue hydrogen, brown hydrogen, yellow hydrogen, turquoise hydrogen, and pink hydrogen.
Pink.
It's more than 4. But isn't hydrogen a colorless gas? Yes, hydrogen is a colorless gas. Hydrogen is an invisible gas, so why so many colors? Well, green hydrogen is the one produced with no harmful greenhouse gas emission. So electrolysis. So we use electrolysis to make green hydrogen, but is it electrolysis? The problem with green hydrogen is how do they make the electricity for electrolysis? Is it green? No, so green hydrogen is not that popular because they have to use electricity, and that electricity is probably made from burning coal. So it's not really green, it's deceptive. Blue hydrogen is produced mainly from burning natural gas. Or actually reacting natural gas. Okay, so that's not so green, probably because that's going to make CO2. Gray hydrogen is created from natural gas or methane and steam reformation. Black and brown hydrogen use coal. Pink hydrogen, this is it. It's not red hydrogen, it's pink hydrogen. Pink hydrogen is generated through electrolysis powered by nuclear energy. Nuclear produced hydrogen can be referred to as purple hydrogen or red hydrogen. So red, purple, and pink hydrogen are the same, I guess. So this is the big thing. Yellow hydrogen would be great. Yellow hydrogen would be produced through solar power, photovoltaic. My friend was working on that. My friend was trying to generate a photovoltaic cell powerful enough to electrolyze water to generate hydrogen gas using solar energy. So most of those Teslas are powered by coal, really.
Yeah.
Yeah. Well, I guess not. Tesla's not the only electric vehicle now. A lot of people don't care. A lot of people don't care where the electricity comes from. They just think it's green or not so green. Even California has an initiative for green, and so we could be buying not green electricity, but from a company that makes green electricity. So all they have to do is make a little bit of green, but they can sell brown, and then we'll call it green. And then you pay the full price. This is a whole big controversy right now about California's electric grid. And because California is paying high prices, but are they really getting green electricity? And when you look at it, when peak demand's there's not enough green electricity.
As you're heading up to Mammoth Mountain,
Yeah.
Which interstate is that where there's like a lot of solar
14.
panels? Yeah.
Yeah.
I can imagine, I even see lots being advertised to buy in. I can imagine.
Near California City. Well, out to Las Vegas, there's that one huge solar farm that only lasted 2 years. Now it's already obsolete. That one was using high temperature to generate
I'm sure
electricity.
people will buy land and use it as
Place these solar farm.
Yeah.
Well, that's great. Although these wind turbines, right now there's a big environmental issue with the wind turbines. The wind turbines are generating lots of waste. They're trying to figure out what to do with these wind turbines because they're too expensive to recycle. And so they just go into landfill right now. And so even though this is supposed to be so green, it's turning out to be not so green. And so anyway, this is a big, in chemistry right now, green chemistry is very big. You know, and lots of people are thinking about these issues here, and so you know, it's a progress. Anyway, that's it for the time. So that's batteries. This is a brief introduction to batteries, brief introduction to electrolytic cells. You don't need to know too much about that. And then we're going to have skeleton redox. So skeleton redox I'm going to cover on Monday, and that would be it for the new stuff. We'll end up stopping here.